Hello, Math 113. Welcome to part 2 of our discussion of vectors. And I'd like to pick up exactly where we left off. Remember, we talked about writing vectors in terms of the unit vectors I and j, where I is the horizontal and j is the vertical unit vectors. And then if you look at this here, your A1 is the horizontal component, kind of like your magnitude in the horizontal direction, and your B1 for vector v is your vertical direction component. So if you have two separate vectors, v is A1i, it's hard to say, plus B1j, and w is A2i plus B2j. To add the vectors together, it's so much easier than using the tail to tip method to find the resultant. So notice all you do is add the A values together for each vector, and then to get the J component, you add the B values together right there, okay? And then to subtract, you would subtract those. So what is this replacing? So I don't know if you watched the last video. If you have a vector, let's just say v, looks like this, okay? And let's say w looks like that. To add those together, the tail to tip method, you would have to pick up w right here in red and put it at the tip of vector v. And then your resultant vector is the vector from the initial point on the first vector to the terminal point on the second vector. So this is the resultant. But if you have the vector as a linear combination of the unit vectors I and j, then you can simply add the horizontal component, the A values, and the B values. Okay? All right. So do we have an example? Of course we do. So first example for part 2 video, which is example D, if you're doing the whole lecture, we want to add v plus w. Okay? So if I add the vector v, remember if we write that on paper, this is the proper notation with a directed line segment on top because we can't do bold. Then I'm going to write the vector v in its component form, 2i minus 5j. Okay, we're adding that to negative I minus 6j. And then I want to add the I values together. Now, if I use the formal definition, it says 2 plus a negative 1i. So again, I've got my A values that I'm adding together. And that'll be plus negative 5 plus a negative 6j. So in that case, I am adding my B values together, signs included. Okay. Now when I finish that up, 2 plus a negative 1 is 1i. Negative 5 plus a negative 6 is plus a negative 11j. But if I write that completely simplified, you don't have to have the 1 times I minus 11j. Now, likely you're taking this test online, but maybe not. You don't necessarily have to show me all these steps. Honest to goodness, if I was doing this, I would just say 2i plus a negative I is 1i. Negative 5j plus a negative 6j is negative 11j. It's that simple. What I did with all these steps is just showed you using the formula. So next, if I do v minus w, why don't you go ahead and do that one and pause it and do that on your own. Okay, so if I write this in detail, v 2i minus 5j minus w, which is negative I minus 6j. Okay, now if I follow the formal definition that I had on the previous page, right here, v minus w is a1 minus a2 with the I on the outside, b1 minus b2 with the j on the outside. That's what I'm going to use. Okay, so that's going to be 2 minus a negative 1. Again, this coordinate, okay, no, the I goes on the outside, okay, plus And then we have negative 5 minus a negative 6, j on the outside. So 2 minus a negative 1 is 3i. Negative 5 plus 6, right? These two negatives turn positive. So that's going to be plus j. And that's my final answer. Now, another way to approach that, I'm going to squeeze this in right in the middle. You could say 2i minus 5j. This negative, distribute it. So that'd be plus I plus 6j. Add your i's, 2i plus 1i is 3i. Negative 5i plus 6j is 1j. Okay, so either way you think about it works. You can easily perform scalar multiplication in terms of I and j if you have the vector v equals ai plus bj, and you would like to multiply that by k. Then essentially you are multiplying the a value times k and the b value times k. Easy enough. So example E here asks you to do that with two different problems. I would love for you to pause it right now and multiply negative 7 times the vector w. And then if you feel confident about that, then come over here to the next example and multiply 4 times the vector w, and then subtract 3 times the vector w. And I hope that went well for you, so let's do this. So if I multiply negative 7 times the vector w, again, let me write this with proper notation. This is what it looks like if you write it on paper, whereas this is what it looks like if it's typed. So that really just means do negative 7 times 2i minus 5j. And you can think about that as the distributive property. You multiply each one of these coordinate values by negative 7, so that's negative 14i plus 35j, right? Easy enough. 4w minus 3v, so that's going to be 4. I'm going to take out that first step where I wrote it in just handwriting form. 4, I'm going to go ahead and type in w. Negative I minus 6j, write in w rather, and then 3 times v, which is 2i minus 5j. So when you multiply a vector times a scalar, it really does work like the distributive property. That's negative 4i minus 24j. Here, I'm going to distribute that negative 3. So it'd be negative 6i plus 15j. Negative 4i minus 6i is negative 10i. Negative 24j plus 15j is going to be negative 9j. Really just like adding like terms. Okay? Easy breezy. All right, so there is a zero vector, and it has 0 magnitude, and direction is not really valid because it has 0 magnitude, and it can be written as 0i plus 0j, and that is in that component form as a linear combination of I and j. And let's talk about some properties. Properties of vector addition. So notice the first one's called the commutative property. Why? Because you're commuting u plus v. You would get exactly the same value if you added v plus u. Think about why that might be the case. Okay. Here, associative property, if you add u plus v plus w, and on the left side you added u plus v together first and then added w, and on the other side you added v plus w together first and then you did u plus v plus w, you would get the same result. So it doesn't matter how you group your vectors together. Of course, when you add 0 to any vector, you just get that 0. You just get that vector. I said that wrong. So u plus 0 does equal u. It doesn't matter if the 0 is in the front or the back. And if you add u to a negative u, you do get the 0 vector. Now, I'm not going to prove these. Okay, we would leave that to a basic linear algebra class where you get to prove something like this, but they're really not hard proofs. If you were, let's look at the first one. If you said u was defined to be the vector ai plus bj, okay, and v, let's just say, is the vector ci plus dj, okay, instead of getting into a1, b1, that sort of thing. Well, by definition, u plus v, if I use the definition for addition, would be A plus CI plus B plus DJ. That's just the definition of vector addition. All right. Now, is it okay with you if we change A plus C to C plus A? And you should say, of course it is. Why? Because when you add numbers together, they commute. We know 2 plus 3 is the same as 3 plus 2. That's the commutative property of real numbers, not of vectors. This is just dealing with real numbers. And I can do the same thing on this side and write that, also in parentheses, is D plus BJ. And then by definition, you notice that the V vector values are first, C and D. So that would be vector V, by definition, plus, or actually let me back up one step. Let's make that more clear. That's going to be CI plus DJ plus AI plus BJ. So that's the vector addition backwards, which would give me, ignore all these lines in between, this would give me vector V plus vector U. End of proof. Now all the proofs work very similarly, using properties of real numbers in the operations and applying that to vectors. I know you don't want to be bored out of your mind proving these four, and then there's even more after this, so I'm going to leave the proofs off, but I wanted you to see, just in case you're curious, why that is true, and maybe an idea of how you could prove the others if you needed to. And I'm not finished with the properties either. There's properties of scalar multiplication. So check out what we're doing here. If you've got two scalars, CD times the vector U, you are allowed as an associative property to multiply D times the vector U first and then multiply that times C. Okay? And depending on your situation, you might need one or the other version of that. There is a distributive property with the scalar multiple. I kind of used it already. But you have C times U plus V. That's going to be C times U plus C times V. I told y'all you could do that, but really it wasn't official that you could do that yet when I did it earlier. And what problem am I referring to? Hold on just a minute and I'll show you. Here's the problem E that I was referring to. When you have negative 7 times 2i minus 5j, what I was supposed to do using the definition was actually this. It's negative 7 times 2i and then plus negative 5, negative 7's first, times negative 5j. Well, I just jumped right here and did negative 7 times 2 is negative 14i, and negative 7 times negative 5 is 35j. Okay, so we do have a distributive property, but it's actually using just multiplication of real numbers to get there. And notice the third property, I've got a pen issue. The third property is different than the second one. Notice this, the second one is the you're distributing a scalar. The C value is just a number like 5 or negative 3 or pi. Okay? The third property, you're distributing the vector. So the vector U in the back, you can multiply it or distribute it inside when you're adding two scalars together. Okay? It makes sense, the multiplicative identity number 4. If you multiply, that is the vector 1 times U, you just get U. It would be true for the scalar also. I do believe that's supposed to be a scalar 1 and not bold like that. Which I guess it wouldn't matter if you bolded it or not. That's just the number 1 times U is U. 0 times the vector U gives you the 0 vector. Again, notice that this 0 is not bold because it's not the vector 0. It's just the number 0 times the vector U is equal to the vector 0, right? Which is 0i plus 0j in that component form. All right, magnitude property. What's that saying? If you're trying to find the magnitude of a scalar times a vector, you can just take the absolute value of the scalar value times the magnitude of the vector. And that actually showed up in the earlier in the lecture as well. Now we have a definition of a unit vector. Remember when I talked about the definition of a unit vector in the part 1 video, and I said it's really not defined yet, but it just means the length is 1. Here's where it's finally defined in the textbook. But a unit vector is defined to be a vector whose magnitude or its length, let's call it magnitude, is 1 unit long. Now, how do you find a unit vector? All right, so for any non-zero vector v, the vector v, notice what this is, v divided by the magnitude of v, is the unit vector that has the same direction as v. Okay, so let's take that in. All right, so if you take the vector v, all right, and you divide each of its components by the magnitude of v, then you're going to have a vector that is 1 unit long or has a magnitude of 1 unit. Okay, so basically you take v and you divide it by its magnitude. Now let's do that. Yes, example F, let's do it. So it says find the unit vector in the same direction as v equals 5i minus 12j, then verify that the vector has a magnitude of 1. Okay, so we're supposed to find the unit vector v. All right. So v is 5i minus 12j. Okay, I'm even supposed to be putting these little guys over the I and j because those are vectors I and j, but y'all, I get so tired of that. It gets old and looks really, really messy. But those are vectors, so I can't bold them when I'm just writing by hand, so I really used to be putting those little lines over it. Okay, so I'm supposed to find the magnitude of vector v. Remember how to do that? You square the I component, which we often call that as A, plus you square the J component, which is negative. When you find the magnitude, I's and J's do not belong in that calculation. Okay, only the A value and the B value. So that's square root of 5 squared is 25, plus 12 squared is 144. That gives me the square root of 169, which last I checked, I believe was 13. So the magnitude of vector v is 13. Now what am I supposed to do with that? I'm supposed to calculate vector v over the magnitude of vector v. So I've got 5i minus 12j divided by 13. Now, supposed to leave it like that. That means divide each component by 13. So it's 5 over 13i minus 12 over 13j. Again, forgive me. I really should be putting these directed line segments over that to denote that I and j are vectors, but I just can't make myself do that every time. Or make it bold, which looks like a big mess too. So just know, please know that I and j are unit vectors, and I'm just too lazy to write those things over it every single time. Okay, now here's where things get fun. To be able to write a vector in terms of its magnitude and direction, notice v is going to be a non-zero vector, and theta is a direction angle. So let's talk about, we've got this vector drawn in like a standard position, starting at the origin, okay, and pointing outward. The direction angle is this value, come on, highlight, right there. So notice it goes from the positive x-axis to the angle. That value's got to be between 0 and 360 degrees, or 0 and 2 pi if you're talking about in terms of radians, okay, has to be. It's measured from the positive x-axis to v, just like I said. And then the vector can be expressed in terms of its magnitude and direction angle as, okay, we've got v, notice that's the magnitude of v, times cosine of theta, times that I, which is the unit vector in the horizontal direction, plus the magnitude of v times sine of theta, j, which is the component in the y direction. Now, why would that work? Why in the world are we going from, there was no trig at all, right, in this part 1 of the video, and 19 minutes into part 2, and then suddenly I'm throwing trig in again. All right, remember you've got an angle going on, so that's screaming trig anyway. And you can break this down into its components. Remember, I goes this way, j goes this way. But how long is that, right? Remember, cosine is your x value, and sine is your y value, right? This is what we've been talking about this whole trig class. So that's why this works. You need to commit that guy to memory right there. It'll look very familiar compared to the last few sections that you've been working with. I don't think this is any big stretch compared to what you've been doing so far, okay? All right, so for example G, let's see if we can use this information, okay? So the wind is blowing at 30 miles per hour in the direction of south 45 degrees west. We're supposed to express its velocity as a vector v in terms of I and j. Now let's write our formula down. I think that's going to help a lot. So we've got the vector v is equal to the magnitude of v times the cosine of theta times the I unit vector, which I'm supposed to put my little directional line segment over that, plus the magnitude of vector v times the cosine of theta times the j unit vector. That's the formula we're trying to use. Do we have enough information to use it? Well, look, I've got this 45 degrees situation going on here. So the question is that my directional angle or not? Okay, now we've also got 30 miles per hour. That's my magnitude. I feel good about that. That is my absolute, well, my magnitude of V. I like to call that absolute value, but it's not. Okay. We know that the magnitude of V is 30 miles per hour. I'm just going to use 30 in my problem. But what about that directional angle? Okay, remember our directional angle is supposed to start at the positive x-axis and go to the vector. Well, where's south 45 degrees west? Well, we're talking bearing there, right? Y'all learned bearing. Okay, so remember that this guy's north, south, east over here, west over here. All right, so if I'm going south, that means I go south first, I go down first, and then I go 45 degrees in the west direction. So south first, and then 45 degrees in the west direction. That's that angle right there. Okay, now that is not a directional angle. How do I find that? Remember, that's supposed to go from, if we pretend like this is the positive x-axis, which it might as well be towards east, and I go to here, that's my directional angle, theta. That's what I'm supposed to be using, not 45 degrees. Well, how do I find that angle? Well, I don't know. We'll see from west to south down here, that's 90 degrees, right? So that means this little bit here is 45, and we know that all the way around is 180. So we have 180 plus 45 degrees, if you choose to think about it that way, is 225 degrees. Some of you just noticed right off the bat, don't ask me what's happened to my tablet, I don't know, right off the bat that was 225 degrees, that angle down there. For me, I have to think about it a little bit harder than that. So that's my directional angle. Hey, so now I can just plug this in my formula, right? Let's do it. Okay, so I've got the vector V is equal to the magnitude of V, which is 30, times the cosine of 225 degrees I, plus 30 times the sine, almost wrote cosine again, let's don't do that, times the sine, of 225 degrees J. You know why I'm making that sound? Because this is wrong. That's sine of theta. I know y'all noticed that. You were screaming at me for the last 5 minutes how wrong that was. Hey, let me make sure I have it typed up over here correctly. I'm pretty sure I do. Of course. Okay, so that's right. I just wanted to make sure that I didn't have it typed wrong in several locations. That's just me writing wrong. So there it is. That's an I and J form. Now, they would like us to simplify that. Okay, now you got to be careful in the homework. Sometimes they want you to simplify this to exact real values, and sometimes they want you to simplify this using decimals. Let's give them an exact answer right now. Okay, so this is the pen quit working. Here we go. The vector v is 30 times the cosine of 225 degrees. Can we calculate that without using our calculator? Of course we can, right? We're in quadrant 3 over here. You're right here. I think about this as 5 pi over 4 because I think in radians and not in terms of degrees, but that would be 225 degrees. What is the cosine value there? Well, it's negative for one thing, right? How about negative square root of 2 over 2? All right, plus 30. You know what? Sine is negative over here in quadrant 3 also, and it's that over 4, or the 225 degrees, which is also negative square root of 2 over 2. Don't forget your j. Okay, if I simplify that, that's going to give me 30 and 2 cancel, so negative 15 square root of 2i. And then the 30 and the 2 cancel here also negative 15 square root of 2j. And that's the exact answer. Sometimes the homework requests that you round to a certain value, and you could just type that in your calculator. As a matter of fact, if you were asked to round, I would go right back up here and type those values in my calculator instead of trying to evaluate on the unit circle. All right, let's take a look at example H. Okay, it says a vector is described, express the vector v in terms of I and j. And that really was the truth for the last problem too. The directions just read a little different, but we're still just trying to write the scenario as a vector. So a child pulls a sled along level ground by exerting a force of 30 pounds on a handle that makes an angle of 45 degrees with the ground. Okay. It says he pulls a sled. So let's just say this is the ground. There we go. Now I'm going to draw you a sled that's just going to be this flat thing, not really a sled. We're not make it pretty or anything. And 45 degrees. Okay, and then there's a kid right here pulling the sled. Woohoo! All right. What do you think? A child pulls a sled along level ground by exerting a force of 30 pounds on a handle that makes an angle of 45 degrees. So 30 pounds is what we have going on right here. Now, if it helps, every time I suggest you do this, even if you think it doesn't help, write down your formula that you're using. So we're trying to write this in terms of I and j. That's what it says right here. How do we do that? Remember, we got a vector v. And it is the magnitude of the vector v times cosine of theta times the I unit vector component, which I'm supposed to put a little directional vector above there, plus the magnitude of v times the sine of theta times the unit vector j. That's the formula that I'm using. Do I have enough information? I should say I do. Okay. Now here's something I need you to think about. So this kid is pulling a sled, right? Not pushing the sled. So it says a child pulls a sled along level ground exerting a force of 30 pounds on a handle that makes an angle of 45 degrees. Where do I put that arrow? That's what I'm asking you. So do I put it down here? That would mean the kid's pushing the sled, right? So the arrow goes right here. That really does matter in terms of the direction your force is going. So we're doing 45 degrees this way. So I think we've got everything we need. You've got the vector v. Now that is 30. Our magnitude of the vector v is 30. And then we have cosine. Would that just not be 45 degrees? Isn't this one easier than the last one? If you think about this, this is already in terms of an XY axis. Let me find a different color here. You know, there's our XY axis. There's X, there's Y. So that is a directional angle. It's not like dealing with bearing and we have to adjust it. Okay? All right, so 30 cosine of 45i plus 30 sine of 45j. Now again, I don't read anything in these directions about rounding, which means I need to carry on with an exact answer. So my vector v is 30. We know that the cosine of 45 degrees, because we have this memorized right, we're in quadrant 1. That's pi over 4 if you like. Cosine is the x value there. That is square root of 2 over 2 times I plus 30, and then square root of 2 over 2j. And then I simplify this. This is looking a whole lot like the last problem, isn't it? So this is 15 times the square root of 2i plus 15 times the square root of 2j. That is my vector v in terms of I and j. Okay, now I have reached the 30-minute mark, and I always like to shut these things down, at least more recently, in 30 minutes so I don't overwhelm you. You can take a break and go get something to eat or walk around the block. Clear your head. I don't have a bunch of examples left, but they're all application problems, so they're not quick, okay? I'm hoping I'll wrap this up with a part 3. I'm even hoping part 3 won't be in the entire 30 minutes, but please don't be mad if it is. I hope you have a great day. If you don't come back until another day to wrap this up, go ahead and get started on the homework. If you're done with lecture, go ahead and get started, see how far you can get, and then come back for the application problems. Hope you have a wonderful day.